So let's look at another diagnostic plot. Here we have plot the residuals versus each of the x variables. That sounds like a lot of work, and it is. So the goal is to search for evidence of nonlinear relationships in X that might not be modeled in the model and therefore show up in the residuals. We should ideally not see a pattern anywhere, and as usual, if it hits us over the head, then we have to do something. I'm using simulated data here from the following model, and you see it's a linear model. It can be totally fit by linear regression, even though there's a square here, because it's linear in beta. That being said, it is quadratic in X. It's a linear model, but it's quadratic in X. And a little bit of error here. So the third variable is an indicator variable, which will show up in the plots. As an analyst, I don't know this function, because if I did know, I wouldn't do any regression. I'd just use the function. So I don't know about the function, and I run the linear regression with all the variables available, y on x1, x2, x3. All right, I get some output. I look at the r squared. Brilliant, 96%. Gee, that is really, really good. We are one happy camper or campers. So something is significant, blah, blah, blah. This can be interpreted. We don't attach a meaning to x1, x2, x3, and so forth. But the estimates are biased because, well, we omitted one term. And so if you look at x2, there's 12. x2, 3. That's wrong. That's way wrong. And the constant is minus 17. Here the constant is 0. That's way wrong. So let's look at the diagnostic plot now. We have 3 x variables, 3 diagnostic plots. I will start with the third. This is an indicator variable. It only has 2 values. Oh, I put it onto 0 and 10, right? So usually we put it 0 and 1. Doesn't matter, right? It's 2 values. We can't see much from this because there are only 2 values. So it's hard to get a nonlinear relationship from 2 estimates of means. So here we see what we always want to see, namely nothing. You can frame this and put it up on your wall and title it nothing. And here we take a step back and get hit over the head. That's definitely quadratic, right? That's plain as can be. You're not going to get anything more beautiful than that. So let's add the variable in there. So I'm generating the square here, new variable, that's the square, adding it to the regression, la-ti-da-ti-da. Our r squared has gone to 99.9%. Here you can already see that this is not a real data set because this just doesn't happen in real life. Even 96% wasn't really real. So, and the reason why it's high, it's a few variables. We got the model right, and there's little variation here. So let's look at the coefficients. Do they look better? So, well, we know it's unbiased theoretically. The coefficient here was 2. Here we have 1.95. If we add the standard error, totally in line. Here we have 3. There we 3.17. If we subtract the standard error, totally in line. Here we have 1. And this is the square down here, 0.991. With standard error, totally in line. -1. And then the standard error in there. Well, we might need 2 standard errors here. Totally in line. Where's the intercept? It's back to 0 or mostly 0. With standard error, we don't even need a full standard error. So this makes a lot of sense. It works. In practice, if you have a lot of x variables, you can reasonably do this for all variables. And you may even have more than 100 x variables, right? So what you do is you do that for x variables you particularly care about, that you're particularly suspicious about, or maybe an x variable that turns out to be really, really important to your findings. So you want to double check that there isn't some other effect. Quadratic effect is the obvious one usually. Yes. So the other thing is the simulation showed very clearly, it was a beautiful example, if I may say so, of this technique. When in practice with real data, I mean, you can find it sometimes, but it's not often really as obvious as it was in this example. Okay, that brings me to the end of this session.